Chapter 1, Introduction to Environmental Science, including key themes, concepts, and examples for each section. Chapter 1, Introduction to Environmental Science 1.1 Defining Environmental Science. What is environmental science? Study of interactions between humans and natural systems, air, water, soil, biodiversity. Goals: understand environmental problems, develop solutions, promote sustainability. Differentiated from ecology, focuses on organisms and ecosystems, and environmentalism, activism. Core questions: how do human activities alter Earth systems? How can we balance resource use with ecological integrity? Case study: the role of environmental science in addressing the Flint water crisis, lead contamination. 1.2 Interdisciplinary nature of the field, integration of disciplines, biology, ecosystem health and biodiversity. Chemistry, pollution analysis and toxicology. Geology, soil and mineral resource management. Economics, cost-benefit analysis of environmental policies. Sociology/political science, human behavior and policy implementation. Example: solving air pollution requires chemists, analyze emissions, engineers, design filters, economists, carbon pricing, and policymakers, regulations. Tools of the trade: remote sensing, GIS mapping, statistical modeling, and citizen science. 1.3 Historical perspectives on environmentalism, timeline of key movements, pre-industrial era, indigenous stewardship practices, e.g., Native American land management. 19th century, conservationists like John Muir, founder of Sierra Club, and Theodore Roosevelt's national parks. 1960s-1970s, rise of modern environmentalism, Rachel Carson's Silent Spring, 1962, and the birth of the EPA, 1970. First Earth Day, 1970, and the Clean Air/Water Acts. 1980s present, global awareness, e.g., Brundtland Report, 1987, Rio Earth Summit, 1992. Key figures: Aldo Leopold, Land Ethic, Wangari Maathai, Green Belt Movement, Greta Thunberg, Climate activism. Lesson: environmentalism evolved from local conservation to global systemic change. 1.4 Key global environmental challenges: climate change, rising sea levels, melting glaciers, and shifting weather patterns. Biodiversity loss, sixth mass extinction, habitat destruction, invasive species, and overexploitation, e.g., Amazon deforestation. Pollution, plastic waste in oceans, PM2.5 air pollution, and chemical runoff, e.g., dead zones in the Gulf of Mexico. Resource depletion, overfishing, aquifer depletion, and soil degradation, e.g., Dust Bowl parallels. Inequity, disproportionate impacts on marginalized communities, e.g., climate refugees, toxic waste dumping in low-income areas. Emerging solutions, Paris Agreement, 2015, circular economy models, and rewilding initiatives. Chapter 1 Summary: Environmental science bridges knowledge and action, rooted in interdisciplinary collaboration and historical lessons. By understanding humanity's role in ecological crises and the tools to address them, readers gain a foundation to engage with subsequent chapters on specific systems, threats, and solutions. Chapter 2, Earth Systems and Processes 2.1 The atmosphere, structure and function, structure, layers, troposphere, weather, 0 to 12 kilometers, stratosphere, ozone layer, 12 to 50 kilometers, mesosphere, meteor burns, 50 to 85 kilometers, thermosphere, auroras, 85 to 600 kilometers. Composition, 78% nitrogen, 21% oxygen, trace gases, CO, argon. Functions: protection, ozone layer absorbs UV radiation, greenhouse gases, CO, methane, regulate temperature. Climate versus weather, climate, long-term patterns, weather, short-term changes. Human impacts, ozone depletion, CFCs and the Antarctic ozone hole, case study, Montreal Protocol success. Climate change, rising CO levels, reference IPCC 2023 report on warming trends. 2.2 The hydrosphere, water cycles and ocean systems, water cycle, processes, evaporation, condensation, precipitation, infiltration, runoff. Reservoirs, oceans, 97%, glaciers, 2%, groundwater, 0.6%. Ocean systems, currents, thermohaline circulation, Great Ocean Conveyor Belt, Gulf Stream's role in Europe's climate. Challenges, ocean acidification, pH decline due to CO absorption, sea level rise, case study, Maldives vulnerability. Freshwater issues, scarcity, Aral sea shrinkage, irrigation impacts, aquifer depletion in India. 2.3 The geosphere, plate tectonics and soil formation, plate tectonics, boundaries, divergent, mid-ocean ridges, convergent, Himalayas formation, transform, San Andreas fault. Natural disasters, earthquakes, 2011 Doku, volcanoes, Mount Pinatubo's climate impact. Soil formation, processes, weathering, mechanical, chemical, organic matter accumulation. Horizons, O, organic, A, topsoil, B, subsoil, C, parent material. Human impacts, erosion, Dust Bowl, 1930s, versus modern deforestation in the Amazon. Mining, resource extraction and land degradation, Appalachian mountaintop removal. 2.4 The biosphere, life's interconnected web, ecosystem dynamics, food webs, energy flow, producers to apex predators, keystone species, wolves in Yellowstone. Symbiosis, mutualism, bees pollinators, parasitism, tapeworms. Biodiversity, threats, habitat loss, Amazon deforestation, invasive species, cane toads in Australia. Conservation, rewilding efforts, European bison reintroduction. Gaia hypothesis, Earth as a self-regulating system, James Lovelock. Chapter 2 Summary Earth systems atmosphere, hydrosphere, geosphere, and biosphere interact dynamically to sustain life. Human activities disrupt these systems, but scientific understanding and policy, e.g., Montreal Protocol, offer pathways to resilience. Case studies like the ozone recovery and Doku's tectonic shifts highlight both vulnerabilities and solutions. Discussion questions: 1. How might melting polar ice, hydrosphere, affect atmospheric circulation patterns? 2. Why is soil health critical for the biosphere and human agriculture? Further reading, The Sixth Extinction by Elizabeth Colbert, Biosphere. This Changes Everything by Naomi Klein, Climate Policy. This chapter integrates foundational science with contemporary challenges, emphasizing interconnectedness and interdisciplinary solutions. Chapter 3, Ecology and Ecosystems 3.1 Principles of Ecology, Definition: Ecology studies interactions between organisms and their environment. Levels of organization: organism, population, community, ecosystem, biome, biosphere. Key concepts: biotic versus abiotic factors, living, predators, plants, versus non-living, temperature, pH, elements. Ecological niches, role of a species in its ecosystem, e.g., decomposers, pollinators. Competitive exclusion principle: two species cannot occupy the same niche indefinitely. Case study: Darwin's finches in the Galapagos Islands, adaptive radiation and niche specialization. 3.2 Ecosystem dynamics, energy flow and nutrient cycles, energy flow, food chain/webs, producers, plants, primary consumers, herbivores, secondary consumers, carnivores. 10% rule, only 10% of energy transfers between trophic levels. Nutrient cycles, carbon cycle, photosynthesis, respiration, fossil fuel combustion. Nitrogen cycle, fixation, by bacteria, nitrification, denitrification. Phosphorus cycle, weathering of rocks, uptake by plants, runoff into water systems. Human impacts, eutrophication from excess phosphorus, e.g., Gulf of Mexico dead zone. Disruption of carbon cycles via deforestation and fossil fuels. 3.3 Biomes of the world, major biomes, tropical rainforest, high biodiversity, nutrient-poor soils, Amazon deforestation case study. Desert, low precipitation, specialized flora, e.g., cacti and fauna, e.g., camels. Tundra, permafrost, low-growing plants, Arctic warming and methane release. Grasslands, savannas, African herbivores, versus temperate prairies, soil erosion risks. Aquatic biomes, freshwater, lakes, rivers and marine, coral reefs, open ocean. Threats, coral bleaching, Great Barrier Reef, overfishing, Atlantic cod collapse. Human-altered biomes, urban ecosystems and agricultural monocultures. 3.4 Biodiversity, importance, threats, and conservation, why biodiversity matters, ecosystem services, pollination, water filtration, carbon sequestration. Resilience, diverse ecosystems recover faster from disturbances. Threats, habitat loss, deforestation, Southeast Asian palm oil plantations. Invasive species, zebra mussels in the Great Lakes. Climate change, shifting ranges, polar bear habitat loss. Conservation strategies, protected areas, Yellowstone National Park. Corridors, linking fragmented habitats, jaguar corridors in Central America. Captive breeding, California condor reintroduction. Global efforts, CITES, regulates wildlife trade. Svalbard Global Seed Vault, preserving crop diversity. Chapter 3 Summary Ecology reveals the intricate web of life, from energy flow in food webs to the resilience offered by biodiversity. Biomes showcase Earth's diversity, yet human activities threaten these systems. Conservation from local habitat restoration to global treaties offers hope for sustaining ecosystems. Discussion questions: 1. How might disrupting the nitrogen cycle affect agricultural productivity? 2. Should conservation prioritize keystone species, e.g., wolves, or entire habitats? Further reading: The Diversity of Life by E. O. Wilson, Biodiversity. Braiding Sweetgrass by Robin Wall Kimmerer, Indigenous Ecological Knowledge. This chapter bridges ecological theory with real-world challenges, emphasizing the urgency of preserving interconnected life systems. Chapter 4, Natural Resources, Use and Management. 4.1 Renewable Resources, Forests, Fisheries, and Solar Energy. Definition: resources replenished naturally over short time scales. Forests, ecosystem services, carbon sequestration, habitat provision, soil stabilization. Threats: deforestation, Amazon loses 17% since 1970, illegal logging. Solutions: reforestation, bond challenge, certification, FSC. Fisheries, overfishing, 34% of global fish stocks overexploited, FAO. Sustainable practices, aquaculture, marine protected areas, Great Barrier Reef. Case study: Atlantic cod collapse, 1990s, versus Alaskan salmon management success. Solar energy, potential, 173,000 terawatts strike Earth daily, 100x global energy use. Innovations, photovoltaic efficiency gains, from 15% to over 22% in a decade. Case study: Germany's Energiewende, renewables supply 46% of electricity, 2023. 4.2 Non-renewable resources, fossil fuels and minerals, fossil fuels, environmental costs, CO emissions, 36 billion tons/year, oil spills, deep water horizon. Peak resources, oil reserves may last 50 years at current rates, BP Statistical Review. Case study, Alberta tar sands, carbon-intensive extraction, habitat fragmentation. Minerals, extraction impacts, acid mine drainage, habitat loss, e.g., lithium mining in Atacama Desert. Rare earth elements, China controls 60% of production, used in renewables tech. Transition strategies, carbon capture, Iceland's Carbfix, mineral recycling. 4.3 Water resources, availability, scarcity, and management, global distribution, 2.5% fresh water, 70% locked in ice, 1.1 billion people lack safe water access, WHO. Scarcity drivers, climate change, Cape Town's 2018 Day Zero crisis. Pollution, agricultural runoff, Mississippi River dead zone. Management, technology, desalination, Israel meets 80% of domestic water via seawater. Policy, India's Jal Shakti Abhiyan, water conservation campaign. Case study, Singapore's NE Water, recycled wastewater meets 40% demand. 4.4 Sustainable resource extraction and circular economy, sustainable practices, forestry, reduced impact logging, Gabon's FSC certified operations. Mining, urban mining, recovering metals from e-waste, 7% of global gold supply. Circular economy, principles, reuse, Patagonia's worn wear, recycle, EU's 55% packaging waste target by 2030. Case studies, Ellen MacArthur Foundation, promotes circular design, e.g., modular smartphones. Japan's Top Runner program, mandates energy-efficient appliances. Challenges, economic incentives favoring linear models, consumer behavior. Chapter 4 Summary Balancing resource use with sustainability requires innovation, solar tech, desalination, policy, certification, quotas, and systemic shifts, circular economy. Renewable resources demand careful management to avoid overexploitation, while non-renewables necessitate phased transitions. Water scarcity underscores the need for equitable governance. Case studies highlight both pitfalls, cod collapse, and progress, Germany's renewables, offering actionable lessons. Discussion questions: 1. Can solar energy fully replace fossil fuels without exacerbating mineral scarcity? 2. How might circular economy principles apply to your local community? Further reading, The Water Will Come by Jeff Goodell, Water Scarcity. Cradle to Cradle by William McDonough, Circular Design. This chapter bridges resource science, policy, and ethics, urging readers to rethink consumption in an era of planetary limits. Chapter 5, Pollution and Environmental Degradation 5.1 Air pollution, causes, effects, and solutions. Causes: anthropogenic, fossil fuel combustion, vehicles, power plants, industrial emissions, chemicals, particulates, agricultural practices, ammonia from fertilizers, and waste incineration. Natural: wildfires, e.g., 2020 Australian bushfires, volcanic eruptions, and dust storms. Effects: health: respiratory diseases, asthma, COPD, cardiovascular issues, and 7 million premature deaths annually, WHO. Environmental: acid rain, pH 5.6, smog, e.g., Delhi's PM2.5 levels 400 g/m superscript 3, and climate acceleration, CO, methane. Solutions: policy, Clean Air Acts, carbon pricing, and emission standards, e.g., Euro 6 norms. Technology: scrubbers, electric vehicles, and renewable energy transitions, e.g., Norway's EV adoption. Case study: China's Blue Sky campaign reduced Beijing's PM2.5 by 35%, 2013-2021. 5.2 Water pollution, contaminants and remediation. Contaminants, chemical, heavy metals, mercury in Minamata Bay, pesticides, DDT, and pharmaceuticals. Biological, pathogens, E. coli in Flint water crisis, and algal blooms, Lake Erie's microcystins. Physical, plastics and sediment runoff, Great Barrier Reef siltation. Effects, biodiversity loss, Chesapeake Bay dead zones, human health risks, cholera outbreaks, and ecosystem collapse. Remediation, engineering, wastewater treatment, Singapore's NE water, and bioremediation, oilating bacteria. Policy, EU Water Framework Directive, US Clean Water Act. Case study, Ganges River Cleanup, Namamai Ganj Initiative, tackles sewage and industrial waste. 5.3 Soil degradation and land use conflicts, degradation drivers, erosion, deforestation, Haiti's 98% tree loss, and overgrazing, Sahel desert expansion. Chemical damage, salinization, Indus Valley farms, pesticide overuse, and heavy metals, Chernobyl exclusion zone. Land use conflicts, urban sprawl versus farmland, California's Central Valley, mining versus indigenous lands, Amazon's Yanomami territory. Solutions, agroecology, crop rotation, terracing, Andean practices, and organic farming. Policy, UN's Land Degradation Neutrality Fund, Brazil's Amazon Fund. Case study, Ethiopia's Tigray project reversed soil erosion via community-led terracing. 5.4 Plastic pollution and waste management, scope, 8 million tons of plastic enter oceans yearly, microplastics found in Arctic ice and human blood. Impacts, marine life entanglement, sea turtles, ingestion, whales with 88 pounds of plastic in stomachs, and chemical leaching, BPA. Solutions, reduction, bans on single-use plastics, Rwanda's strict policies. Innovation, bioplastics, FA from algae, and circular economy models, Adidas recycled ocean plastic shoes. Case study, EU Single-Use Plastics Directive eliminates 10 top ocean polluting items by 2030. Chapter 5 Summary Pollution and degradation are interconnected crises demanding systemic change. Air and water quality directly impact human health, while soil and plastic pollution destabilize ecosystems. Solutions span policy, global treaties, technology, renewables, bioremediation, and cultural shifts, circular economies. Success stories like Beijing's air cleanup and Rwanda's plastic ban prove actionable pathways exist. Discussion questions: 1. How can developing nations balance industrial growth with pollution reduction? 2. Should corporations or consumers bear greater responsibility for plastic waste? Further reading, Silent Spring by Rachel Carson, Pesticides and Advocacy. The Story of Stuff by Annie Leonard, Consumerism and Waste. This chapter underscores the urgency of addressing pollution holistically, linking local actions to global sustainability goals. Chapter 6, Climate Change and Global Impacts. 6.1 The Science of Climate Change, Greenhouse Effect, natural process where gases like CO, methane, and water vapor trap heat, maintaining Earth's habitable temperature. Human activities amplify this effect by increasing greenhouse gas, GHG, concentrations. Evidence of change, temperature records. Global average temperature has risen 1.2 degrees C since pre-industrial times, IPCC 2023. Ice core data reveal CO levels are higher than in 800,000 years, pre-industrial, 280 ppm, 2023, 420 ppm. Satellite observations, accelerated ice melt in Greenland, 267 billion tons/year lost, and Antarctica. Paleoclimatology, historical shifts, e.g., ice ages, versus current unprecedented warming rates. Climate versus weather, climate is long-term, 30-plus years, weather is short-term. 6.2 Greenhouse gases and human activities, major GHGs, CO, 76% of emissions, fossil fuels, coal, oil, deforestation. Methane, 16%, agriculture, livestock, rice paddies, landfills, fossil fuel extraction. Nitrous oxide, 6%, synthetic fertilizers, industrial processes. Fluorinated gases, 2%, refrigerants, aerosols. Emission sources, energy, 35%, agriculture, 24%, industry, 21%, transportation, 14%. World Resources Institute. Feedback loops, Arctic permafrost thaw releasing methane. Amazon rainforest becoming a carbon source due to deforestation. Keeling curve, CO levels at Mauna Loa Observatory show steady rise since 1958. 6.3 Consequences, rising temperatures, sea levels, and extreme weather, temperature rise, projections, 1.5 degrees C 4.4 degrees C by 2100, depending on emissions, IPCC scenarios. Heatwaves, 2021 Pacific Northwest Heat Dome, 49.6 degrees Celsius in Canada. Sea level rise, 20 centimeters since 1900, up to 1 m by 2100. Threats to coastal cities, Miami, Jakarta. Case study, Tuvalu plans digital nationhood as rising seas engulf islands. Extreme weather, hurricanes, increased intensity, Hurricane Ian, 2022. Droughts, 2022 Horn of Africa crisis, 20 million at risk. Secondary impacts, ocean acidification, pH drop 0.1 since 1850. Biodiversity loss, coral bleaching, Great Barrier Reef, 50% decline since 1995. Social impacts, climate refugees, 21.5 million displaced annually, UNCR. Food insecurity, crop yield declines in tropics. 6.4 Mitigation and adaptation strategies, mitigation, renewables, solar/wind now cheaper than coal in 90% of the world, IRENA. Carbon pricing, $170/ton CO needed by 2030 for net zero, IMF. Reforestation, Trillion Trees Initiative, restore 350 million hectares. Policy, Paris Agreement, 196 nations, limit warming to 1.5 degrees Celsius. Adaptation, infrastructure, Netherlands floodgates, Delta works, Bangladesh's cyclone shelters. Agriculture, drought-resistant crops, Simit's maize varieties. Community resilience, indigenous-led fire management, Australia. Climate justice, loss and damage fund, 27 Colombian pesos, for vulnerable nations. Case study, Bhutan's carbon negative status. Chapter 6 Summary Climate change, driven by human activities, disrupts ecosystems and societies through rising temperatures, sea levels, and extreme weather. Mitigation, renewables, reforestation and adaptation, resilient infrastructure, equity-focused policies, offer pathways to safeguard futures. Urgent action is critical, but feasible. Discussion questions: 1. How might feedback loops, e.g., permafrost thaw, accelerate warming beyond current projections? 2. Should wealthy nations compensate vulnerable countries for climate impacts? Further reading, The Uninhabitable Earth by David Wallace Wells, Impacts. Drawdown by Paul Hawken, Solutions. Visual aids, diagram, enhanced greenhouse effect. Graph, CO concentrations, Keeling curve. Map, global sea level rise projections. This chapter blends scientific rigor with actionable hope, emphasizing interconnected global responsibility. Chapter 7, Environmental Policy, Ethics, and Justice. 7.1 International Agreements. Key agreements: Paris Agreement, 2015 aims to limit global warming to 2 degrees Celsius, ideally 1.5 degrees Celsius, through nationally determined contributions, NDCs. Challenges include enforcement and varying national commitments, e.g., U.S. withdrawal in 2017, re-entry in 2021. Sustainable Development Goals, SDGs Goals 13, Climate Action, 14, Life Below Water, and 15, Life on Land, intersect with environmental sustainability. For example, Costa Rica's reforestation program aligns with SDG 15. Montreal Protocol, 1987 successful phase-out of ozone-depleting substances, Kigali Amendment targets hydrofluorocarbons, HFCs. CITES, regulates wildlife trade to protect endangered species, though enforcement gaps persist. Challenges and successes. Success, global CFC reduction restored ozone layer by 1.3% per decade. Failure, limited progress on SDG 14, ocean conservation, due to overfishing and plastic pollution. 7.2 National and Local Environmental Governance National Policies, U.S. Clean Air Act, reduced air pollution by 78% since 1970 but faces rollbacks under shifting administrations. European Green Deal, aims for carbon neutrality by 2050, with policies like the Carbon Border Adjustment Mechanism. China's 2060 Carbon Neutrality Pledge, heavy investment in renewables but criticized for coal plant expansion. Local initiatives, urban sustainability, Copenhagen's goal to be carbon neutral by 2025, San Francisco's Zero Waste Program. Grassroots efforts, community solar projects in Germany, Kenya's plastic bag ban, 2017. Governance challenges, federal versus state conflicts, California's vehicle emission standards versus federal preemption attempts. Public participation, NGOs like Greenpeace influence policy, youth movements, e.g., Fridays for Future. 7.3 Environmental ethics. Ethical frameworks, anthropocentrism, prioritizes human needs, e.g., dam construction displacing ecosystems for energy. Ecocentrism, values ecosystems intrinsically, Aldo Leopold's land ethic advocates for a community including soil and water. Deep ecology, Arne Nice radical ecocentrism, emphasizing biospheric equality. Cultural and religious perspectives, indigenous stewardship, Morakaishia Katanga, guardianship, in New Zealand's Whanganui River rights. Religious teachings, Pope Francis's Laudato Si calls for ecological conversion in Catholicism. Ethical dilemmas, development versus conservation, Amazon rainforest deforestation for agriculture in Brazil. Animal rights, factory farming ethics versus food security needs. 7.4 Environmental justice and equity. Core issues, environmental racism, marginalized communities, e.g., Louisiana's Cancer Alley, face disproportionate pollution. Global inequity, Global South contributes least to climate change but suffers most, e.g., Bangladesh's flooding. Case studies, Flint water crisis, lead contamination in a majority black city highlights governance failures. Standing Rock protests, indigenous resistance against Dakota Access Pipeline, 2016-2017. Solutions, policy reforms, US EPA's EJ 2020 Action Agenda, EU's Just Transition Mechanism. Grassroots movements, Sunrise Movement's climate justice advocacy, Kenya's Wangari Maathai Green Belt Movement. Emerging challenges, climate refugees, 21.5 million displaced annually, UNCR, lack of legal protections. Corporate accountability, lawsuits against Shell, 2021, for climate inaction set precedents. Chapter 7 Summary. Environmental policy, ethics, and justice are intertwined in addressing global crises. International agreements set frameworks, but national/local governance determines implementation. Ethical debates shape priorities, while justice movements demand equity. Success hinges on integrating science, ethics, and inclusive policy making. Discussion questions. 1. How can international agreements better hold nations accountable? 2. Should ecocentrism override economic growth in policy decisions? Further reading, This Changes Everything by Naomi Klein, Climate Justice. Silent Spring by Rachel Carson, Ethical Advocacy. Visual aids, Map, Global Climate Vulnerability Index. Timeline, Key Environmental Agreements, 1972-present. This chapter underscores the need for ethical, equitable, and enforceable policies to bridge the gap between planetary health and human justice. Chapter 8, Sustainability and Sustainable Development. 8.1 Principles of Sustainability. Definition: the integration of environmental, economic, and social equity, the triple bottom line, to meet present needs without compromising future generations. Brundtland Commission, 1987. Development that meets the needs of the present without compromising the ability of future generations to meet their own needs. Core concepts: ecological footprint, human demand versus Earth's regenerative capacity, e.g., overshoot since the 1970s. Carrying capacity, limits of ecosystems to support populations, e.g., overfishing depleting marine stocks. Circular economy, moving from take-make waste to reuse/recycle models, e.g., Patagonia's Worn Wear program. Case study: Bhutan's Gross National Happiness Index prioritizes sustainability over GDP. 8.2 Green technologies and renewable energy. Renewable energy sources: solar, photovoltaic panels. Global capacity surpassed 1 TW in 2022. Wind, offshore farms. UK's Hornsea project powers 1 million homes. Hydro, pumped storage systems. China's Three Gorges Dam. Geothermal, Iceland meets 90% of heating demand via geothermal. Emerging tech, green hydrogen, EU's REPowerEU plan. Carbon capture and storage, Norway's Northern Lights project. Challenges: intermittency, battery storage innovations like Tesla's Megapack. Resource extraction for tech, e.g., lithium mining impacts. 8.3 Sustainable agriculture and urban planning. Agriculture, regenerative practices, cover cropping, no-till farming. Rodale Institute's 40-year trials show 40% higher yields. Agroecology, integrating biodiversity. Mexico's Milpa system. Vertical farming, Singapore's Sky Greens reduces land/water use. Urban planning, green cities. Curitiba's BRT system, 75% of commuters use public transit. Smart cities, Barcelona's IoT-enabled water/energy efficiency. Sponge cities, China's flood-resilient infrastructure, e.g., Wuhan. Case study: the Netherlands Farm of the Future combines tech and ecology. 8.4 Individual and community action. Individual steps: reduce meat consumption. 1 kg beef equals 27 kg CO. Energy conservation: LED bulbs save 80% energy versus incandescent. Sustainable fashion, thrifting, brands like Reformation. Community initiatives: transition towns, Totnes, UK, local currency, renewable co-ops. Urban gardens, Detroit's 1,500 community gardens. Zero waste movements, Kamikatsu, Japan recycles 80% of waste. Policy advocacy, youth-led campaigns, Fridays for Future. Citizen science, e.g., eBird for biodiversity tracking. Chapter 8 Summary: Sustainability requires systemic shifts from renewable tech and regenerative farming to mindful consumption and inclusive governance. While challenges like resource limits and inequity persist, global innovations, Iceland's geothermal, Singapore's vertical farms, and grassroots efforts, Kamikatsu's zero waste, prove viable pathways. Discussion questions: 1. Can green tech fully decouple economic growth from environmental harm? 2. How might urban design prioritize both sustainability and social equity? Further reading, Donut Economics by Kate Rayworth, Redefining Growth. The Future We Choose by Christiana Figueres, Climate action. Visual aids, infographic, circular economy versus linear economy. Chart, global renewable energy adoption, 2020-30 projections. This chapter bridges theory and practice, urging collective action to align human systems with planetary boundaries. Chapter 9, Case Studies in Environmental Science. 9.1 Success Stories, Ozone Layer Recovery and Costa Rica's Reforestation. Ozone layer recovery. Background: in the 1980s, scientists discovered a hole in the ozone layer due to chlorofluorocarbons, CFCs, from aerosols and refrigerants. Key actions: Montreal Protocol, 1987 Global Treaty phasing out CFCs, ratified by 197 nations. Industry shifts to alternatives like hydrofluorocarbons, HFCs, later targeted by the Kigali Amendment. Outcomes: ozone hole over Antarctica is healing, projected full recovery by 2060. Prevented an estimated 2 million annual skin cancer cases. Lesson: proactive international cooperation can reverse environmental harm. Costa Rica's reforestation. Background: by the 1980s, deforestation had reduced forest cover to 21%. Key actions: payment for ecosystem services, PEAS landowners paid to preserve forests, ban on deforestation without permits, 1996, goal to be carbon neutral by 2050, outcomes: forest cover rebounded to 54% by 2021, ecotourism now generates $4 billion annually. Lesson: economic incentives and policy enforcement drive conservation. 9.2 Ongoing crises, deforestation in the Amazon and coral reef decline. Amazon deforestation, drivers, cattle ranching, soy farming, and illegal logging, accelerated under Brazil's recent policies. Impacts: loss of 17% of the rainforest since 1970, threatens 10% of Earth's biodiversity. Indigenous communities, e.g., Yanomami, face displacement and violence. Global repercussions: the Amazon now emits more CO than it absorbs in some regions due to degradation. Coral reef decline, causes: warming oceans, 1.5 degrees Celsius rise since 1900, acidification, and pollution. Impacts: Great Barrier Reef, 50% coral loss since 1995, 91% damaged by 2022 bleaching. Threatens 25% of marine species and coastal communities reliant on fisheries. Solutions: marine protected areas, coral nurseries, and reducing agricultural runoff. 9.3 Innovations, solar power in Iceland and vertical farming. Solar power in Iceland. Context: despite its geothermal dominance, Iceland invests in solar to diversify renewables. Innovation: solar panels optimized for low light conditions, paired with hydrogen storage. Impact: aims for 100% renewable energy by 2040, exports green tech expertise. Vertical farming. Examples: Singapore's Sky Greens, produces 1 ton of veggies daily on 0.1 hectares. Aerofarms, USA uses 95% less water than traditional farming. Benefits: reduces land use, transportation emissions, and pesticide reliance. Challenges: high energy costs, limited crop variety. 9.4 Lessons from disasters, Chernobyl and Deepwater Horizon. Chernobyl nuclear disaster, 1986, cause: reactor meltdown due to design flaws and human error. Environmental impact, 4,000 plus km superscript 2 exclusion zone, radioactive contamination persists in soil/wildlife. Paradoxical biodiversity surge, e.g., wolves, lynx, in the absence of humans. Legacy: strengthened nuclear safety protocols, e.g., IAEA regulations. Deepwater Horizon oil spill, 2010, cause: blowout of BP's Macondo well, 4.9 million barrels spilled into the Gulf of Mexico. Impact: 11 deaths, 1,300 miles of coastline polluted, $65 billion in cleanup/fines. Long-term damage to marine life, e.g., dolphins, deep-sea corals. Reforms, U.S. offshore drilling regulations tightened, rise in oil spill response tech. Chapter 9 Summary case studies reveal both humanity's capacity to heal ecosystems, ozone recovery, Costa Rica, and the consequences of negligence, Amazon, Deepwater Horizon. Innovations like vertical farming offer hope, while disasters underscore the need for vigilance. Each story reinforces core themes: policy matters, equity is essential, and resilience requires learning from past mistakes. Discussion questions: 1. How can the Montreal Protocol's success inform today's climate negotiations? 2. Should Chernobyl's wildlife sanctuary status influence post-disaster land management? 3. What ethical dilemmas arise when balancing economic growth, e.g., Amazon soy, with conservation? Further reading: The Ministry for the Future by Kim Stanley Robinson, Climate Solutions. The Ends of the World by Peter Brannan, Mass Extinctions. Visual aids, map, Amazon Deforestation Hotspots, 2020-23. Infographic, Coral Reef Bleaching Triggers and Solutions. This chapter bridges theory and reality, urging readers to apply lessons from history to forge a sustainable future. Chapter 10, The Future of Environmental Science. 10.1 Emerging Technologies, Carbon Capture and Lab-Grown Meat, Carbon Capture and Storage, CCS, Direct Air Capture, DAC technologies like Climeworks, Iceland, and Carbon Engineering, Canada, remove CO from air. Costs remain high, $600/ton, but falling. Carbon utilization, converting CO into concrete, carbocrete, or synthetic fuels, Prometheus fuels. Challenges, energy intensity, scalability, and ethical concerns, e.g., fossil fuel companies using CCS to justify continued extraction. Lab-grown meat, process, cultivating animal cells in bioreactors, e.g., Memphis Meats, Mosa Meat. Benefits, 90% lower GHG emissions, 99% less land use versus conventional livestock. Barriers, consumer acceptance, regulatory hurdles, and energy demands. Case study, Singapore's approval of Eat Just's lab-grown chicken, 2020. 10.2 The role of AI and big data in environmental monitoring, applications, climate modeling. AI improves prediction accuracy, e.g., Google's DeepMind forecasting rainfall 6 hours ahead. Biodiversity tracking, AI analyzes camera trap images, wildlife insights, and acoustic data, rainforest connection. Pollution mapping, satellite data and machine learning identify methane leaks, GHG-SAT. Case studies, Global Fishing Watch, uses AI to monitor illegal fishing via vessel tracking. Planet Labs, daily satellite imagery tracks deforestation in real time. Challenges, data privacy, algorithmic bias, and accessibility gaps in low-income nations. 10.3 Educating the next generation of environmental stewards, curriculum innovations, interdisciplinary programs, combining STEM with ethics, policy, and indigenous knowledge, e.g., Stanford's Earth Systems program. Experiential learning, citizen science projects, eBird, iNaturalist, and school sustainability clubs. Digital tools, virtual reality, VR, to simulate climate impacts, e.g., melting ice VR experience. Gamification, e.g., Echo a game teaching ecosystem management. Global initiatives, UNESCO's Education for Sustainable Development, ESD, framework. Youth-led movements, Fridays for Future, Earth Uprising. 10.4 Envisioning a Resilient and Equitable Future, Principles for Resilience, Equity-Centered Design, Prioritizing Marginalized Communities in Climate Adaptation, e.g., Bangladesh's Floating Schools. Decentralized Systems, Community Solar Microgrids, e.g., Puerto Rico post-Hurricane Maria. Biomimicry, designing cities inspired by nature, e.g., Singapore's City in a Garden. Case studies, Bhutan, carbon-negative nation via forest conservation and renewable energy. The Green New Deal, vision for a just transition to a sustainable economy. Barriers to overcome, political short-termism, corporate lobbying, and global inequity. Hopeful visions, donut economics, balancing human needs with planetary boundaries, Kate Rayworth. Regenerative cultures, indigenous-led restoration, e.g., Morokai Katanga in NZ. Chapter 10 Summary. The future of environmental science hinges on innovation, carbon capture, AI, education, and equity. Emerging technologies offer promise but require ethical oversight. AI and big data empower precision in monitoring, while reimagined education fosters stewardship. A resilient future demands systemic shifts, decolonizing environmentalism, centering justice, and merging cutting-edge science with ancestral wisdom. Discussion questions: 1. Could lab-grown meat inadvertently harm traditional farming communities? 2. How can AI avoid reinforcing existing power imbalances in environmental governance? 3. What would a regenerative economy look like in your region? Further reading: The Future We Choose by Christiana Figueres, Actionable Optimism. Braiding Sweetgrass by Robin Wall Kimmerer, Indigenous Wisdom. Visual aids, infographic, Carbon Capture Pathways, DAC, VIX, Mineralization. Timeline, AI's Role in Environmental Science, 2010-2040. This chapter closes with a call to action. The future is not predetermined, it is shaped by choices we make today. Appendices Appendix A, Key Environmental Terms and Concepts, Alphabetical Glossary of Critical Terms introduced in the book. Biodiversity, the variety of life in ecosystems, essential for resilience and ecosystem services. Carbon footprint, total greenhouse gas emissions caused by an individual, organization, or product. Circular economy, economic system minimizing waste by reusing, repairing, and recycling materials. Ecosystem services, benefits humans derive from ecosystems, e.g., pollination, water filtration. Greenhouse effect, natural process where gases trap heat in the atmosphere, intensified by human activities. Sustainable development, meeting present needs without compromising future generations, Brundtland Commission, 1987. Tragedy of the Commons, overexploitation of shared resources due to individual self-interest. Additional terms, Anthropocene, biomimicry, carrying capacity, climate justice, ecological footprint, mitigation versus adaptation, permaculture, Appendix B, further reading and resources curate list for deeper exploration, books, Silent Spring by Rachel Carson, Pesticides and Environmental Advocacy. The Sixth Extinction by Elizabeth Colbert, Biodiversity Loss. Braiding Sweetgrass by Robin Wall Kimmerer, Indigenous Ecological Wisdom. Donut Economics by Kate Rayworth, Redefining Economic Growth. Reports and articles, IPCC reports, climatechange.ch. The Lancet Planetary Health, peer-reviewed journal. UN Sustainable Development Goals, SDGs.un.org. Documentaries, Our Planet, Netflix, Biodiversity and Conservation. An Inconvenient Truth, Climate Change Awareness. Kiss the Ground, Soil Regeneration and Agriculture. Organizations, World Wildlife Fund, WWF Conservation Initiatives. Intergovernmental Science Policy Platform on Biodiversity and Ecosystem Services, IPBES. Environmental Defense Fund, EDF Policy and Advocacy. Online tools, Global Footprint Network, footprintcalculator.org. iNaturalist, Citizen Science Biodiversity Tracking. Appendix C, Exercises and Discussion Questions. Chapter Aligned Activities to Reinforce Learning, Chapter 1, Introduction to Environmental Science, Discussion, Debate the ethical implications of prioritizing economic growth over ecological preservation. Exercise, calculate your ecological footprint using an online tool and propose 3 reduction strategies. Chapter 5, Pollution, Case Study Analysis, research the Flint water crisis. What systemic failures occurred, and how could they be prevented? Hands-on, conduct a local water quality test, pH, turbidity, and compare results to EPA standards. Chapter 8, Sustainable Development, Role-play, simulate a UN negotiation to balance renewable energy adoption with mineral resource equity. Project, design a circular economy model for your school or workplace. General exercises, debate, should corporations pay reparations for historical environmental harm? Fieldwork, map local biodiversity in a park or neighborhood using iNaturalist. Educator notes, include rubrics for grading projects and tips for facilitating inclusive discussions. Adapt exercises for virtual or in-person settings, e.g., virtual debates, at-home lab kits. Formatting notes, Appendix A, bullet-pointed terms with concise definitions. Appendix B, categorized by type, books, reports, documentaries, with brief descriptions. Appendix C, structured by chapter, mixing theoretical and hands-on activities. Accessibility, highlight open access resources, e.g., IPCC reports, iNaturalist. Suggest low-cost alternatives for exercises, e.g., DIY water testing kits. This structured approach ensures clarity, engagement, and practicality, empowering readers to apply environmental science principles in diverse contexts.